Hi and welcome to my video series on the trapezoidal rule. I'm going to break this up into 2 or 3 parts. So they'll be short, sharp videos, but based on different areas of content. And the final one, we're really going to bring it together and give you and present to you the trapezoidal rule. But let's start with this function. So here's a function, and it's a y and x designation. And so I've sketched it here. It's pretty rough, but it's the function y equals negative x squared plus 6x plus 1. I've designed it very particularly like that, and so it's a bit of a complex looking quadratic, but I've done this deliberately because I really wanted it to be sort of heading up in this direction, but slowing down. It gives us a good space to work with, so it's a nice function to work with for this question I'm going to pose. So imagine for a second that I drew a little dotted line down here. There we go, and I'm going to say, just for ease sake, that that is the point 4, even though I've drawn a really bad 4 there. 4. I want to know, what's the area under here? Now the good news is this topic is going to lead towards an understanding of how to calculate that area. But in the meantime, we're going to look at how we could approximate that area and what we could do. So before we lead into the trapezoidal rule, I'm going to talk to you about the initial steps of approximation, and this is actually really important for the theoretical approach that we'll do later on. So what if we approximated just by getting smaller parts of areas? Because this bit here, this is a straight line, and this is a straight line, so that's pretty good. This is curved, that's a straight line as well. This is curved, that's a bit of a problem. So it's the curve, it's approximating under the curve that's kind of the problem. So what if I recognise, first of all, there's some stuff I know about this function. So first of all, I know that this is 1. And in fact, this is the coordinate 0, 1. And what if I drew some dotted lines down here? There, you probably already guessed what they represent. That's 3, that's 2, and that's 1. Okay, what if I drew some dotted lines? And what if, in green, I considered some rectangles within that? But first, let's determine these coordinates. At 1, what does y equal? Negative 1 squared plus 6 times 1 plus 1 is 6. So it's 1, 6. I hope I've got that right. And what happens at 2? Negative 2 squared plus 6 times 2 plus 1 is 9. So we get 2, 9. What happens at 3? Negative 3 squared is negative 9 plus 18 plus 1 is 10. I get that right? Yes. And 4, what happened to 4? Negative 4 squared is negative 16 plus 6x, so 6 times 4 is 24 plus 1 is 25 minus 16 is 9 again. So that's a 4. I'm really struggling with 4s today. 4, 9. So actually it goes back down after 3, but we'll deal with that, that's fine. So what I've got here is a quadratic function split into 4 parts, and I know the coordinates of where 1, 2, 3 and 4. So I'm splitting up into slices. These coordinates are really important. So what I could do, and I'll do one in blue and one in pink, and we'll talk about them, is I can actually work out the area of a whole bunch of different rectangles. So this is called the upper rectangle method. I'm building these rectangles here, and I know that each rectangle has a width of 1. I've chosen some nice easy numbers. And this rectangle has a height of 6. This rectangle here has a height of 9. This one has a height of 10. This one has a height of 9. And so my area for the upper rectangle method is equal to 6 times 1 plus 9 times 1 plus 10 times 1 plus 9 plus 9 times 1. And that of course is equal to 15, 25, 34. That's my upper rectangle method. I could also do my lower rectangle method, which I'll do in pink, and that is, what about if I cut the rectangles here and here at the lower ordinate, there and there. So now this one will have a height of just 1 because of that height there, and this one will have a height of 6, and this one will have a height of 9, and this one will have a height of 10. And so my area for my lower rectangle method will be 1 times 1 plus 6 times 1 plus 9 times 1 plus 10 times 1. And of course that's 26. So you could reasonably suggest that maybe a good approximation would be an average of these two. And so my average, which is sometimes referred to as my middle rectangle, would be 34 plus 26 over 2, which is equal to 30. So that would be a fairly good approximation, certainly better than 34 and 26, because we can see the 34 approximation includes all these overestimates here, 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 and the 26 approximation includes all these underestimates here, here. So actually, by suggesting an average, it's probably going to help us out a lot. We could also get that average by being a bit clever, and instead of using 1 as a height or 6 as a height, we could just split the difference and use 3.5 as a height. Instead of 6 and 9, we could use 7.5. And instead of 9 and 10, we could use 9.5, and this would also be 9.5 again. And when you add all those up, you'll get 30 as well. So there's a lot of different ways that we could do and approach the middle rectangles method. But that said, hopefully you can see here that irrespective of how you do the rectangle method, there's always going to be some inaccuracy. The middle rectangle method is actually very good, particularly for quite simple functions, but it's not perfect. Now, just as a discussion base, and this is something you'll probably end up considering in class anyway, is how could we make this more accurate? Well, the obvious answer, I believe, is to just have more rectangles. So we split that into 0 to 0.5 to 1 to 1.5 to 2 to 2.5, etc. Create more rectangles, you're going to create more accuracy. And we'll talk more about that, because the theoretical approach will be, well, what happens if we create infinitely many rectangles? I'll let you think about that before we get there. Anyway, so that's the rectangle method. I'm going to talk to you now about the trapezoidal method.